Okay, now that we have seen how to do 3 regions for a lossless material, let's do 3 regions with a lossy material. We have exactly the same system where we have region number 1, region number 2, and region number 3, and our electric and magnetic field are incident on our layered material, normally incident in the same direction. We do exactly the same thing that we did before. We put an origin for 3 here, an origin for 2 here, minus D2 on the left-hand side, and O1 here on the right-hand side. We start with exactly the same thing we did before. Z3 at O3 is equal to eta 3, but there's one difference. Eta 3 used to be strictly real. Now eta 3 is complex. And this is equal to Z2 at O2. That's because ohms cross the boundary just like they did before. Then we do again exactly the same thing where we normalize by eta 2 and we plot it on the Smith chart. So right here is our real, let's say this is our real value and our imaginary value. Right here is Z2 normalized at O2. Now we need to get to minus D2, so we're going to again rotate towards the generator. This is towards the generator, a distance D2. So from the center, we start here, and we go a distance D2 towards the generator. So this is Z2 normalized at minus D2, rotating towards the generator, a distance minus D2. This distance and this right now are exactly the same, but we aren't finished. The next thing that we need to do is accommodate the e to the minus alpha z in this problem. E to the minus alpha z represents how much loss we have as we go from left to right, but not only do we go from left to right, we also go from right to left. So we have e to the minus alpha z twice, so this is an e to the minus 2 alpha z term. What does this change? It certainly changes the impedance that we see. It also changes the reflection coefficient. And the reflection coefficient is the easiest thing for us to analyze. So Z2 at minus D2 for the lossy case is equal to reflection coefficient at minus D2 for the lossless case times e to the minus 2 alpha z. The alpha value here is in region 2, and the z is D2. So we find this magnitude from this magnitude. This magnitude is what we see right here. This is the magnitude of 2 at minus D2 when it is lossless, no loss. So what we do, here's our reflection coefficient line down here. This is the reflection coefficient. So measuring from the center over to here, we first read the magnitude for the lossless case. Then we multiply it by this number, which is a scalar. It's a scalar value less than 1, and we get some smaller value, reflection coefficient that's lossy. We take this magnitude right here, and we plot it from the center out, just like this. So our corrected point right here is Z2n at minus D2 when we have our lossy environment. So that's a step that you need to include in your calculation as you go from right to left. If this material right here is lossy, you need to reduce the magnitude of the reflection coefficient, and that changes the Z2 at minus D2 that you read. So we next read Z2 normalized at minus D2. We read the lossy case because that's really lossy. Then we denormalize it by multiplying by eta 2, which happens to be complex. That doesn't change our calculation any. Multiply by eta 2. This is now in ohms, right here, and ohms jumps the boundary. So that is equal to Z1 at O1, also in ohms. Now, if I needed to know the reflection coefficient out here for some reason, I would need to rotate from O1 to minus D1, and if region 1 were lossy, I would also need to reduce the reflection coefficient by e to the minus 2 alpha z, just as I had in this case. So as you can see, everything is exactly the same, moving from right to left. allowing ohms to cross the boundary, using the Smith chart to represent propagation, ohms to cross the boundary. We also are using the Smith chart to represent the attenuation or the loss, and we're doing that via the reflection coefficient.